All right, let's talk about one of the most critical and often overlooked parts of Kubernetes, DNS. It's that thing that just works in the background until it doesn't. But honestly, it's the absolute magic that lets our applications find each other in a world where nothing stays in one place for long. Without it, the whole dynamic microservices dream kind of falls apart. So here's our game plan. First, we'll tackle the core problem. How do things even find each other? Then we'll meet the star of the show, CoreDNS. We're going to learn the secret language of Kubernetes service names and then follow a DNS query on its journey and uncover a really sneaky performance trap. After that, we'll get into some advanced patterns and finish up with the good stuff, how to keep it all fast and fix it when it breaks. Okay, so let's set the scene. In Kubernetes, pods are like fireflies. They're ephemeral, they blink in and out of existence, and every single time they're rescheduled, boom, they get a brand new IP address. So if you're old school and you hardcode an IP, your app is going to break the second that pod gets replaced. How on earth do your applications keep track of each other in this constantly shifting world? Well, we used to have a clunkier way of doing things with environment variables, but this created a really rigid system. The service you wanted to talk to had to be up and running before your client pod even started. Any change, you had to restart your pod. It was a mess. The new way with DNS is so much more elegant. It completely decouples everything. A client can look up a service whenever it wants and always get the freshest, most current address. This is what makes Kubernetes so dynamic and resilient. So, the solution to this big discovery problem is a little thing called CoreDNS. The best way to think of it is as your cluster's own internal, super dynamic GPS. It's been the default DNS server for a while now, and it's way more powerful and flexible than its predecessor, KubeDNS. So what exactly is CoreDNS? Well, at its heart, it's the official name server for your cluster's internal domain. That's usually cluster.local. What it does is constantly watch the Kubernetes API. The moment you create or delete a service, CoreDNS sees it and translates that change into a DNS record, all in real time. It's literally the bridge between the world of Kubernetes objects and the good old DNS protocol everyone knows. And the way it works is pretty cool. It's all built around this idea of a plugin chain. When a DNS query comes in, it goes on a little journey. First, the Kubernetes plugin checks if it's a request for an internal service. If not, maybe the cache plugin has a recent answer stored to speed things up. And if it's a query for something totally external, like google.com, the forward plugin just passes it along to an upstream DNS server. It's a super clean and efficient pipeline. Now, for all this magic to work, Kubernetes needs a language, right? It relies on a very specific and, this is the important part, a very predictable naming convention. This standard is what lets your apps reliably find each other without ever needing to know a single IP address. And this is what that language looks like. Every single service gets what's called a fully qualified domain name, or FQDN. Let's break it down real quick. You've got the name of your service, the namespace it lives in, and then this standard suffix, svc.cluster.local. So if you have an auth service in the backend namespace, its full name becomes authservice.backend.svc.cluster.local. And that predictability, that's everything. Kubernetes uses this naming scheme to create different kinds of DNS records for different jobs. The most common is the A record for a standard service. That points to a single virtual IP that handles load balancing. But then you have something really cool called a headless service. It doesn't give you one IP. It gives you the IPs of all the individual pods behind it. Perfect for when you need to talk to them directly. SRV records help you find specific ports, and an external name service is just an alias, a CNAME, that points to an outside service, like a managed database. Okay, now for something really interesting. It seems like a tiny detail, but how a pod asks for a DNS name can have a massive impact on your cluster's performance. There's a default setting that can create a serious bottleneck, and it all boils down to one little number. And that number is 5. What's so special about 5? Well, inside every single pod, in a config file called /etc/resolv.conf, there's a setting called ndots, and its default value is 5. This tiny setting is meant to make our lives easier, but oh boy, it can cause some serious performance headaches. So here's what that ndots5 rule actually means in plain English. It tells the DNS resolver in your pod, hey, if the name you're looking for has less than 5 dots in it, assume it's an internal service name. So it tries to be helpful by automatically adding on your local search domains first. This is great if you're just looking up Redis, but it creates a huge problem when you're looking up, say, google.com. And this is where the problem hits. Because Google.com only has one dot, which is less than 5, the resolver goes on a wild goose chase. Before it even tries looking up Google.com for real, it fires off all these extra useless queries. It checks for it in the pod's namespace. Fail. It checks the cluster service domain. Fail. All told, it makes 3 extra failed DNS lookups before it finally gets it right. Now multiply that by thousands of requests. You're tripling the load on CoreDNS for no reason, and that can become a performance killer. But wait, there's more. Kubernetes DNS isn't just for simple service lookups. It's actually super flexible and supports some advanced patterns that are absolutely essential for running complex, stateful apps or talking to services outside your cluster. Let's talk about one of the coolest patterns, the headless service. A normal service is like a company's main switchboard. You get one number and it directs your call. A headless service, on the other hand, is like getting a list of direct dial numbers for every single person in the office. By setting cluster IP to none, you're telling Kubernetes, don't give me a virtual IP. Instead, when you query its DNS name, you get back the actual IPs of all the backing pods. This is crucial for things like databases that need to form a cluster and talk to their peers directly. And this is exactly why stateful sets need them. Stateful sets use headless services to create stable, unique DNS names for each of their pods, like database-0, database-1, and so on. So even if the database-0 pod crashes and gets rescheduled on a totally different node with a new IP address, its DNS name stays the same. That name, database-0.my-app, will just point to the new IP. It provides that stable network identity that stateful applications absolutely depend on. Okay, so we've got the what and the why. Now let's get into the how. How do we keep this critical system healthy and performing well, and what do we do when it inevitably acts up? One of the single biggest things you can do for performance is to run the node local DNS cache. This is a game changer. It puts a little DNS caching agent on every single node in your cluster. This means most DNS queries get answered instantly, right from the local node, which takes a huge load off the central CoreDNS servers. And get this, it even helps with some really thorny low-level networking gotchas by upgrading queries from UDP to the more reliable TCP. It's a massive win all around. Oh, and here's a pro tip, a real gotcha you need to know about, especially if you're running Java apps. The JVM has a history of caching DNS results forever. In a static world, that's fine. But in Kubernetes, where IPs are changing all the time, that's a recipe for total disaster. You have to make sure you configure a reasonable TTL, or time to live, so your app doesn't spend hours trying to talk to an IP that's long gone. So when DNS does go sideways, what do? Here's your go-to toolkit. First things first, you have to debug from inside the cluster. So deploy a simple DNS utils pod. Once you're in, take a look at /etc/resolv.conf to see how things are actually configured. You can use nslookup for a quick check, but the real power tool is dig plus search. That command will mimic exactly how your applications behave, including all that tricky ndots logic we talked about. It's the best way to see what's really happening. So when you think about it, DNS is really the unsung hero of Kubernetes. It's the invisible foundation that makes all the dynamic, self-healing magic possible. So I'll leave you with this question. Now that you know about the hidden complexities, the ndots trap, and the caching gotchas, is the DNS in your cluster a silent hero? Or is it a silent bottleneck just waiting to cause an outage?